So as we mentioned at the end of the last video, we're going to talk now about shear and moment diagrams. What these do is these are going to define the shear force and bending moment in a beam as a function of x, x being the length of the beam. And so we're going to define v as it goes along x, and the moment, the bending moment, as that goes along x. So these are going to be, we're going to have, we're going to draw diagrams, we're going to draw graphs, if you will. And what we're going to do is, or what we're going to find is the graphs will be discontinuous and a new cut will be needed every time the loading changes. Now, what causes a loading change? Well, it can be an external force, or let's just say an external load applied. So everywhere that I've got, and those can be things like everywhere I've got a reaction, whether it's a force or a moment, everywhere that I've got a force or moment applied along the beam, and then also a change in a distributed load. Every time I experience, or in between every external load, and so in between every reaction and or applied force, and in between, or at least underneath everywhere that I have a distributed load, and if the distributed load changes, I need a new cut after that change occurs. So sometimes I got multiple cuts, and every time the external load, or every time the loading changes, there's going to be now a new equation that's going to be, we're going to need to find, and we're going to use to construct these diagrams or these graphs. So the procedure step 1, find reactions if possible. Step 2, determine the number of cuts needed. And this is going to be the information you'll use to determine that. Everywhere that you have a loading changed, or the load gets, a particular load gets applied, or a distributed load changes, you'll want to cut in between every loading change. Use equilibrium. Step 3 is use equilibrium to find shear as a function of x and moment as a function of x. for every cut. And then step 4, we're going to graph shear as a function of x and moment as a function of x. And we're going to label any maximum and any minimum bending moments. And this is really what you're after. Why is this important? Well, if the beam is going to fail, or buckle, or break, it's going to occur where I experience a local maximum or local minimum, meaning the largest or the smallest negative value. Where I experience the most bending moment is most likely going to mean I'm going to experience the most stress in that beam, and the stress is what's actually going to cause it to fail. Again, stress is a quantity you're going to talk about in either mechanics of materials or strength of materials course a little bit later after this course. We set the foundation here. Now, something of note here is that the shear is going to be the derivative of the moment with respect to x. And we'll see that in action as we progress along here. Okay. Now, I'm going to do an example related to the previous example that we just worked. Do kind of a simple, we'll do a couple of pretty simple examples here. Lecture 14, page 6 of something. Example. So, similar to what we just worked. Let's put point A. If you hear a cat meowing or a kitten meowing, the universe decided to gift us a new kitten. Interestingly, I'm recording this video at the end of National Kitten Day. We have a new kitten. Her name is Lucille. She is pretty adorable. I probably sound a little disgruntled about it. She's actually pretty cute. I'm sure she'll make an appearance at some point. So if you hear her, that's what you're hearing. Let's see here. Let us apply a 2,000 Newton force along a 12-meter beam right here at 6 meters in the middle. And we'll apply this or we'll put a pin at point A and a roller at point B. And this might look kind of familiar, right? Well, yeah, that's by design. We're basically looking at this guy. Oh, where'd he go? This guy. We're looking at this guy, but instead of dealing with the distributed force, let's just call it a single point force first. And then maybe we'll go back and look at this in distributed form also. But let's look at this as a single point first. Point force first. Okay. What did my procedure say? Go back to your notes. What's the procedure say? What is step 1? Yeah, find your reactions, right? Find your reactions. So go ahead and find your reactions here. Pause if you need to. Okay. Remember from our previous example, and I'm going to line these up pretty close to, as close as I can to each of these free body diagrams. I'm going to line up as close as I can to this overall design. That's going to be by design. All right, remember we found AX to be 0 here. AY is going to be, you'll find AY to be 1,000 newtons, and you're going to find B to be the other remaining 1,000 newtons. Okay, so we need to be able to find those. You set up your equilibrium equations and find those very kind of quickly here. All right. Now what? So we said, okay, that's step 1. Procedure, step 1. Find reactions if possible. Step 2, determine the number of cuts needed. Cuts are going to need to occur in between everywhere that I've got a loading change. So that means an external load is applied, a reaction, or a change in distributed load, or any other applied force. I have an applied force, so I've got reactions here. You can see this on the free body diagram here. I've got reactions here, I've got an applied force, and I've got reactions there. Okay, so how often does the load change? Well, it starts at one point, it changes here, and then it's going to change at the very end also. So basically 2 changes. From here to here is a change, and from here to here is a change. So that means I need to cut in here, and I need to cut in here. You can look at your original diagram and see I've got an applied force. I need to make sure and cut on either side of that applied force. The reactions are at the end, so I don't have to cut on either side of the reactions. You'll see some problems where maybe the roller is over here a little ways, so I would need to cut here, here, and on the other side of the roller. That would give me 3 cuts. But here, the number of cuts is going to equal 2. Okay. Now that's going to be before and after your applied load of 2,000 newtons. And again, anytime I've got an applied load, I need to make sure and put a cut on either side of that applied load. In this case, I just have one here in the middle, so I'm going to make a cut on either side of it. Okay, so I need, that's step 2. How many cuts do I need? Step 3 is I'm going to write equilibrium equations for each cut. Go ahead and draw a free body diagram of the cut, write equilibrium equations. We're going to cut it arbitrarily at some point x in the area where it needs to be cut. And then I'm going to write equations for shear and moment as functions of that x. And then I'm going to draw graphs of those functions. Right, so what does that mean? Well, it means, again, I'm going to cut somewhere in here at some arbitrary distance x from point A. And I'm going to cut in here again some arbitrary distance x from point A. And I'm going to write equations for those. All right, so this is, it's about to start getting a little more intense here. So I'm going to actually stop this video here, start recording the next video, and we'll finish this problem out in the next full video.